Welcome to the Carbon Fibers and Uses webinar. This is our second webinar in the Bitumen Beyond Combustion series. My name is Peter Baudouin and I'm a Senior Advisor with COSIA, and I'll be your host today. Just to give you a little bit of background on the three organizations listed on the top of your screen, Alberta Innovates was the initiator of this project. It's their initiative. Stantec was actually awarded the contract to undertake the study, and COSIA's role is really, once we had seen the report and read it, we really identified that it could be of interest to our innovation community. Hence, we are hosting the call today. We will be recording this call, and I would also like to say, if you do have questions, please look at entering them in the message box, and we will be answering them after the presentation. I'd like to talk or introduce our speakers today. We'll be starting off with Paolo Bombin, who's a Senior Manager with Alberta Innovates, followed by Axel Meissen, Senior Advisor with Alberta Innovates, and finally Nathan Ashcroft, who's a Team Lead with Stantec. As for the agenda today, we're doing about 30 slides, 30 minutes, so we'll be going through them quite quickly. In terms of how the run of show, we'll be starting off with the, of course, introduction, moving on to carbon fibers characteristics. We'll then provide you an overview of the production process and the business case, and then conclude with some insights and conclusions. And then we'll give you a teaser, a little bit of our next webinar. And after that, we'll be opening to questions. On that, I'd like to hand it over to Paolo.
Thank you, Peter, and hello to everyone listening in today, wherever you might be around the world. In the first webinar, we introduced the concept of bitumen beyond combustion. And so before we dive into carbon fibers, I just want to reintroduce the concept and what it's about, just in case we have anyone new on the line who wasn't at the first webinar, to bring them up to speed. So there are two major overarching considerations when looking forward that play to the notion of bitumen beyond combustion. The first is that we have a growing world population. So out to 2050, projections are around 9 billion people on the Earth. And that increase in population will lead to an increase in demand for materials and products over time. Materials and products such as housing, vehicles, and everyday goods. Concurrent with that are mixed projections on the future demand for petroleum-based fuels out to 2050. So beyond 2040, I've seen projections where it's going up, going down, staying static. And so that raises the question that if petroleum-based fuels demand decreases, how can we still derive a maximum value from Alberta's bitumen resource? So bitumen is a constituent of the oil sands. It has a high carbon content relative to other oils, and that presents a unique opportunity to take advantage of to convert bitumen into products, carbon-based products, that the world needs going forward as a way to hedge against any potential drop in demand for petroleum-based transport fuels. These bitumen-derived products and materials would sequester the carbon instead of releasing it into the atmosphere, and that would reduce downstream GHG impacts. These are products and materials that would help diversify Alberta and Canada's economy. It would help create jobs and enable Alberta to maximize the value of its natural resources. So conceptually, that's what bitumen beyond combustion looks like. But practically, on an everyday basis, how would you or I interact with a bitumen beyond combustion product? And so I want to elaborate on that point with a thought experiment. So I want you to imagine that you're leaving work and you have a 10-minute drive home from the office. And in that first minute, you're going to pass by a condo project that's being constructed out of wood. Now that wood is actually has been added to that wood carbon fibers. And the carbon fibers are derived from bitumen. And the carbon fibers are adding strength, rigidity, and lifetime to that condo project. And so that's your first touch point with bitumen beyond combustion. As you drive down the road, you notice that the asphalt on the road looks pretty good and hasn't been replaced in a while. And that's because the asphalt is derived from bitumen. And so that's your second touch point. As you keep driving, you're about 5-6 minutes into your drive, you see a pack of wind turbines on the side with a battery bank at the base. Those batteries are made using vanadium that was extracted from bitumen. Right? And so those batteries are helping to provide electricity in the evenings or when the wind actually isn't blowing. And so for the final 3 minutes of your drive, you sip on your ice cap or your latte through a straw that is biodegradable. The carbon contents of that straw came from bitumen. So there you go. On your 10-minute ride home from work, you've interacted with bitumen beyond combustion products 4 times. And so that's what we see as the future. That's what we see as the vision and the dream here of how we can bring bitumen into daily life through these products. And so to bring it back to carbon fibers, I'm now going to pass it to Axel, who will take us through some background on what carbon fibers are.
Okay, thank you, Paolo. As you just said, I'll speak about basic aspects of carbon fibers and their characteristics. As we all know, carbon is an element that occurs in many different forms, ranging from ultralight and very strong and hard like diamond, to very soft and weak like graphitic lubricants. Carbon fibers is an intermediate form between these two extremes. In carbon fibers, carbon atoms are arranged in long hexagonal chains. In carbon fibers, atoms are arranged in long chains of hexagonal carbon rings. Some bonding occurs between the chains, and some interlocking also occurs between the chains. This structure gives the special properties to carbon fibers. Typically, fibers are 5 to 10 microns in diameter, and then they are spun into threads. These threads can be woven into fabrics, or they can be held together by a binder, such as a plastic or a cement, thereby giving rise to a composite. May I have the next slide, please? The properties of carbon fibers are listed here, and I'd particularly like you to focus on the mechanical properties, namely high strength, high stiffness, good fatigue resistance. And to illustrate these properties, we have given you a couple of links to video clips, and I would like to show the first couple of minutes or so from the first video clip. Okay, so this is concrete reinforced with carbon fibers by means of a strip. And we'll now see the demonstration of the effectiveness of this strip when it is applied on the right-hand side to a concrete beam, 2 meters in length, 5 centimeters by 5 centimeters in cross-section. The first concrete beam doesn't have that reinforcement. I'm going to place it on the ground in a moment and have somebody walk on it very gingerly. And you will see that the beam will break. There it breaks. The weight of the person is likely 50 to 60 kilograms. And now for the same concrete beam, but reinforced with a carbon fiber strip, it's loaded not only by one person, but by several people. And if you can observe the loading on the left-hand bottom, you will see that the beam is still holding up, even though it's loaded to a weight of exceeding 600 kilograms, which is at least a factor of 10 higher than the unloaded and than the unreinforced strip. It also has some flexibility, which is interesting. I'll encourage you to watch the rest of the clip as well as the other clip. So can we go back? Yeah. Okay. I'm now going from the qualitative to the quantitative. Here we list important characteristics of two types of carbon fibers, those made from polyacrylonitrile and those made from pitch. Draw your attention to the numbers for tensile strength and stiffness, which are large numbers, but it's best to see them in relationship to other materials, such as aluminum, steel, Kevlar, and polyethylene. And you will see that the density or the specific gravity of carbon fibers is quite low, comparable to that of Kevlar, but its tensile strength is high, comparable to that of very good quality steels, but its stiffness is very much greater than that of steel. So carbon fibers have these remarkable properties in terms of density, lightness, tensile strength, stiffness, as well as some other characteristics that were shown previously. I'll now hand it over to Nathan in order to talk about production, uses, and the business case.
Thank you very much, Axel. So how do we make these amazing carbon fibers? Well, 90% of carbon fibers made today use the feedstock of propylene, and we'll talk about how that becomes polyacrylonitrile a little bit later on the next slide. And what's emerging here is a route to carbon fibers from propane. About 10% of the market of carbon fibers right now is made from pitch, which is a very heavy oil bottoms feedstock. And what we've discovered in the BBC2 phase 2 study is, considering that oil sands and bitumen is particularly carbon rich, we have a new pathway that we've been exploring, and we'd like to share some more on that on our steps in production. So route 1 on this slide here, conventional crude oil, go through a refinery, a cracker, and we get to propylene, something that's very much established around the world. We go through what's called the BP Sohio technology to acrylonitrile, to a polyacrylonitrile, which is wound. And we go through at the bottom at a very high level here, carbonizing, graphitizing, which are essentially steps to remove impurities and reorder the carbon structure. And we get to, on the right-hand side, an actual carbon fiber, which is wound. On the route 2 here, from natural gas liquids, we get through to a propane. And this is much more of an emerging pathway through a Kasai technology, same pathway. 10% of the market to make carbon fibers, as I mentioned previously, was from pitch. So people have been using a crude oil bottoms, the heaviest, most carbon intensive part of the process, or sometimes a coal tar as well. And they've been looking at this pitch to go through and come into this carbon fiber manufacturing sequence at the bottom, where you have to spin it first and then go through the carbonizing and graphitizing. So with this crude oil bottoms and this intense carbon focus, let's look at a potential route 4 here. So we have bitumen, we have an abundance of bitumen here in Alberta. The heaviest fraction of bitumen is asphaltenes, and I'll talk about that in more detail in the next slide. So where we have an asphaltene, we prepare that in a modified asphaltene, and we go through the same sequence here, spinning, carbonizing, graphiting, till we get to a carbon fiber. So the interesting part here is asphaltene. So let's talk about that on the next slide. Asphaltenes, or as we call it, the true bottom of the barrel, and what makes oil sands unique, bitumen, is approximately approaching 20% of bitumen is actual asphaltenes. Asphaltenes, people have studied these over many, many years. These are complex, rich in aromatics, and they're very complicated compounds. And historically, they've been troublesome, but with our renewed focus here, with the high level of carbon that's in these, we think they've got tremendous potential. Of note, these are very high viscosity. At room temperature, for example, these would be solid. So perhaps the phrase here is asphaltenes have been problematic but rich in potential for us. So on this slide here, and I'd encourage people to look at the phase 2 report. This is really a snapshot of what we're talking about here. So on the left-hand side and on the right-hand side, we're really going through a process where we've got a disorganized compound at the base units, and going through various different heat chemical processes here. We want to get to what we call planar layers. So we're focusing on, through this process here, you can see the high temperatures, alignment and orientation, removal of impurities, and we want to get to what Axel mentioned previously, which gives carbon fibers their strength, which is the layered hexagonal structure. Off on the right-hand side is a visual of what happens there. So we'd have our raw asphaltene moving through these processes of getting them structured, removing impurities through different processes to give us at the bottom right-hand side that hexagonal structure, which really gives us the strength in carbon fiber. So from an asphaltene perspective on technology, where are we at compared to the other feedstock bases? So you can see on the right-hand side here, the Government of Canada technology readiness level, carbon fiber from polyacrylonitrile and propane, and from a common pitch right now is in operation. It's actually happening today. Carbon fiber from asphaltenes, and I'll read this, is we've placed it as a group in the phase 2 report at TRL3. That is to say, we've done an experiment of its function and a proof of concept. People have modified and spun asphaltenes into a raw carbon fiber today, and Paolo will talk about that a little bit later on. So with this in mind, of asphaltene being a great bitumen, oil sands and bitumen and asphaltene being a great source potentially to make carbon fibers, let's talk about the business case that can drive this. Carbon fiber market globally, pretty small, 100,000 tons per annum, growing at a 12.5 compounded annual growth rate. That's a strong compounded annual growth rate, but 100,000 tons for a global commodity is pretty small. For comparative purposes, global steel production in 2016 was 1.6 billion tons. So you can see 100,000 tons to 1.6 billion tons is a significant difference there. Let's look at the cost breakdown of what actually makes a carbon fiber. At a very high level, there's essentially three different components. The feedstock, attributable to 35 to 40%. So we talked about the feedstocks. Then there's the actual process of turning the feedstock into a carbon fiber. That's approximately about 30% of the cost. And then taking that carbon fiber, putting it in a resin, and shaping it to a product that we can use and identify with, that's another 30% of the cost. These are approximate, but it gives us an overview of the different components that make a carbon fiber product. So let's have a look at some of the aspects of how asphaltenes fit in this. There is a couple of oil sands producers that have been removing asphaltenes from their bitumen at their facilities, and to date, asphaltene as a cost has been sold at a coal price. A coal price per ton, approximately, as we did the phase 2 report, was about $40 per ton. If we convert that into pound, which is the numbers we use for current carbon fiber feedstocks, that's 2 cents a pound. So asphaltene, if we removed it, would have a value of about 2 cents per pound. There's a number there for bitumen on line 3, which is associated with a major oil sands production cost of producing a barrel of bitumen. That's just there added for context. So as I mentioned previously, 90% of the carbon fiber market is made from polyacrylic nitrile, or we call PAN. This is the HP stands for high purity. So the US dollars per pound of this commodity starts at about $3 per pound. So as you can see, asphaltene as a feedstock, 2 cents per pound, versus polyacrylic nitrile at $3 per pound, there's a huge differential. And I'll talk about that a little bit more here. So automotive grade carbon fiber currently is about $8 per pound. So that is to say, the carbon fiber that can go into automotive industry, which is a huge part of the steel industry, and we'll talk about that, is $8 per pound. The automotive industry has said, if we could move this number to $5 per pound, i.e. substantially cut out either the feedstock price, the carbon fiber production price, or the end product price, then we can start to move carbon fiber into the automotive industry in a much bigger way, and not just constrained to luxury vehicles. So as you can see here, the work that we've done has led us to a pathway on asphaltenes to carbon fiber, and on the raw cost comparison of asphaltene, it's about 150 times less than polyacrylic nitrile. Now my disclaimer there is we're comparing the raw cost of asphaltene versus a high purity cost of polyacrylic nitrile. But you can see there's a lot of room for maneuver and technology development. There's a big gap to work with. So let's start to look at the potential growth and moving carbon fibers into some big global commodities. And this is actually happening. So let's talk about a few of those. Carbon fiber reinforced concrete. And the image on the right-hand side, we're all familiar with reinforcement steel and concrete. It's a commodity all around the world. You have a look around where you're walking today, you drive home, you commute, we're surrounded by reinforced concrete. With that in mind, it's the largest construction material globally, over 3.5 billion tons per annum of concrete. Approximately 80% of concrete requires reinforcement. That's to say steel reinforcement. People have heard the phrase rebar, reinforcement bar, steel bar. Chopped carbon fibers or short strand carbon fibers in place of reinforcement steel. This is something that's emerging pretty quickly. At a weight of about 2.5%, that is to say a chopped carbon fiber could be a few centimeters in length at the thickness Axel was alluding to earlier. This is mixed in with the concrete, and that is applied in place of steel reinforcement. So we looked at this and we made some analyses on the size of the concrete market globally, the percentage of weight that's inserted. And if 1%, we had 1% of this market was penetrated by 2030, that would represent a demand of 30,000 barrels per day of asphaltenes. So the asphaltenes as a ratio to bitumen was about 20%. So that would be about 150,000 barrels a day of bitumen. So that's pretty significant, and there's a lot of room to grow in that. Why is there some advantages of using carbon fiber with steel? This is, generally speaking, as this is emerging, it has superior operating characteristics to traditional steel reinforcement bar. And I'm just going to cover a few of these. No corrosion of internal reinforcement. It doesn't corrode. So you can imagine that has significant advantages. Post-crack residual strength to concrete, concrete durability, shrinkage reinforcement. These are major issues for the concrete industry globally with steel. So you can see there's some tremendous advantages of carbon fiber in concrete. So that's just one area. The next area we wanted to look at is steel. So as I mentioned earlier, global steel production is also a very large market, 1.6 billion tons, growing to over 2.5 billion tons by 2030. And over on the right-hand side of this slide, we provide a percentage of what makes up that 1.6 billion tons a year. So building and infrastructure, 50% of that market, mechanical equipment, 16% of that market, and automotive, as I mentioned earlier, 13%. So you can see on those top three, 80%, that counters for 80% of the global steel market. We feel the carbon fiber products can start to replace those steel components in an absolutely huge market. And this isn't diluted like concrete was in a percentage of weight. So this calculation, if we just had 1% market penetration of the steel market with carbon fiber, that could represent 500,000 barrels a day of asphaltenes by 2030. Just 1%. And as I mentioned again, and I want to reinforce the point, that's 20% of the bitumen required. So 5 times 500, 2.5 million barrels of bitumen. You can start to see 1% starts to take an awful lot of asphaltenes out of this equation. So let's talk about some of the steel components here that we would replace. We'll be familiar with the steel equivalents of these components, I-beams, U-channels, round tube, flat strips, squares, and so forth. And you can start to see the strength of these components here as well. Perhaps one of the other markets that's really where carbon fiber is really emerging is on the right-hand side. We can see a chassis of a vehicle made out of carbon fiber held by two guys, and unless they're good actors, they don't look like they're straining too much. So it's clearly much lighter. And as you can imagine, the impacts of bringing a vehicle with half the weight and twice the strength, the impacts of that on fuel efficiency and so forth could be profound. So the steel market, we feel, being replaced by carbon fiber products from asphaltenes holds tremendous potential. Another global commodity, carbon fiber reinforced wood. Of course, there's a Canadian advantage here with Canada being a huge producer of wood reinforced products and wood products in general. We did the analysis, and again, I'd refer people back to the Phase 2 report, that this market by 2030 will be 440 million tons per annum. 1% market to this penetration where carbon fiber reinforcement is in the wood. 10% dosage would represent 20,000 barrels a day of asphaltenes. So if you look at that, and we've gone over the advantages on the feedstock from a pricing perspective. We've looked at these global commodities with concrete, with steel, with wood products. There's some tremendous business case emerging here to start to look into this further. With that in mind, to talk about manufacturing locations and some other societal benefications of this, I'll hand you over to Paolo.
Thank you, Nathan, for the taking us through the business case. And so another element of the business case is also manufacturing. And so on the map on the bottom right corner of your screen, you'll see essentially an intensity plot of the different countries around the world and their carbon fiber capacity. So Canada is not a significant manufacturer at the moment. Manufacturing is dominated by the United States, Japan, China, Korea, Taiwan, and a handful of European nations. The current carbon fiber supply chain can be long and complex. And to give you an example, I'd like to describe the supply chain for BMW in Germany for their carbon fibers. It begins in the Middle East, where crude oil is produced. And then that crude oil is then transported to Japan, where it is refined, and we get products such as ammonium propylene that come out. The ammonium propylene, still in Japan, are turned into acrylonitrile, which is then still in Japan turned into polyacrylonitrile. That polyacrylonitrile is then shipped across the ocean to the United States, to the Pacific Northwest, where it is turned into carbon fiber. Once transformed into carbon fiber in the United States, it is flown to Germany for further weaving and component manufacture and final installation in BMW vehicles. And so you can see that is a tremendously long, truly global supply chain. With the potential advantages of using Alberta asphaltenes from bitumen in Alberta for the production of carbon fibers, we could dramatically shrink the length and size of that supply chain. We envision the potential not only of producing the feedstock, but precursor and carbon fiber production in the province, with end product manufacturing in Alberta or elsewhere in Canada. This could supply the entire North American and also some offshore markets with carbon fibers, dramatically reducing the cost and localizing that supply chain. So we see tremendous opportunity here for manufacturing, which would help also to diversify Alberta's economy. Some other considerations as well for carbon fibers, one of them being social acceptance. Carbon fibers are often touted as the material of the next century. They have positive environmental benefits in that they're not, the carbon is trapped in the carbon fibers. It's not being emitted into the atmosphere. And so because of that and because of the tremendous properties that Axel described and the business case that Nathan described, there's really tremendous opportunity for new investment into carbon fibers, the creation of technology jobs, and that all leads to the generation of royalties, taxes, and revenue supporting other industries. So developing a carbon fiber manufacturing and production environment within Canada, we believe would be well received from a social perspective. The one consideration on the environmental side that we need to account for, and Nathan brought it up in terms of production, is the high energy input that's required, the high temperatures that are required for manufacture. So to really make it truly environmental and beneficial, we want to look for low carbon sources of electricity and energy to provide that energy for the carbon fiber manufacturing process. And so to bring it all back together for the whole webinar now, I'd like to share some insights and conclusions to bring it all back. The first being that we really see using asphaltenes from oil sands for carbon fiber manufacturing as a strong win for Alberta, and it's also a strong win when we consider it in the context of another initiative that has very strong interest right now, and that's partial upgrading. So the partial upgrading process, for those that may not be familiar, turns bitumen into a pipelinable product that doesn't require any diluent. To do that, the heavier end of the barrel, there are rejected fractions, and the asphaltenes are rejected in that process. So we're able to make a pipelinable crude that doesn't require diluent, which is a win, and we also now have our feedstock for carbon fibers and asphaltene as the rejected portion of that process. So we see that as very synergistic, the two processes being very synergistic. So that's a strong positive. As I mentioned on the previous slide, the production of carbon fibers and their composites are energy intensive, so we really do want to find those clean sources of energy to help reduce any impacts there. The production of carbon fibers and composites, we've hopefully convinced you, are a major opportunity for Alberta and Canada as a way to diversify our economy and also create new jobs. And finally, I want to mention that for Alberta Innovates, this is a strong priority area, especially within the Bitumen Beyond Combustion program. We will continue to push forward on projects to develop carbon fiber capacity within Alberta, within Canada, so that we're able to, as I mentioned, maximize the value of our natural resources to bring benefits to all Albertans and to Alberta businesses. And so with that, I'd just like to make a mention of a couple more items. The first being that we mentioned on the previous webinar that Alberta Innovates had an open call for the Bitumen Beyond Combustion program. We are not fully through the final contracting phase there, and so unfortunately we can't announce today any of the projects that we've selected, but we do plan on making that announcement during the next webinar, which will be upcoming in January. And so that webinar will be on asphalt and transportation of asphalt product. It will be held on January 31st from 10 to 11 a.m. Mountain Time. Registration is now open. Asphalt is a large global market. It's a growing market. It's something we're going to need into the future regardless. We're always going to be driving vehicles on roads. And so really, this is an area that is of strong interest to the Bitumen Beyond Combustion program because we believe that oil sands bitumen could be a premium feedstock for superior asphalts. So that's one area of interest for us that we're going to discuss in the next webinar. And the other is that, and also quite important, is that currently asphalt is shipped in molten form. And we believe there's an opportunity to actually ship it in a non-molten form, but in a solid form at closer to room temperature. And that reduces the energy demands for that entire process. And so we believe that can be intricately tied to bitumen and to asphaltenes. And so we'll talk a little bit more about that in that webinar. So we hope you can join us. As I mentioned, the webinar registration is open. So head on over there after today's session and sign up for the January event. And with that, I'll pass it back to Peter.
Okay, thanks, Paulo. So we wanted to open up for questions. If you do have them, please put them into the messaging system. I think we have a few queuing up, so we'll ask Carrie to read a few of those out.
Sure. First question is there an example, a building, bridge, or other example in Alberta which has use of BBC carbon fiber?
Do you want me to answer that? I'm unaware of a bridge that incorporates carbon fibers in the case of Alberta. There are bridges and bridge components in the United Kingdom and in Germany. And also in the case of British Columbia, a number of bridges have been reinforced with carbon fiber strips of the kind that I showed early on in connection with the concrete components.
Yeah, I've just recalled. Stantec has been involved in similar projects, as Axel mentioned, here in Alberta, with applying those strips for existing infrastructure. And I believe there's one or two bridges that we know quite well here in Calgary that are under consideration for strips in addition. Yeah, I think it's something that's growing significantly.
Yeah, in BC it's done for earthquake proofing of structures.
Okay, thank you.
In the production process, as indicated in your presented routes 1 through 4, what are the differences in energy input and CO2 EQ output for routes 1 through 3 when compared to route 4?
It's a good question. And in the phase 2 report, we kind of allude to some of this. We expect, for example, the route of 3, the crude oil bottoms or coal tar bottoms, to be similar to the asphaltene route, but the detailed analysis has not been done. But if you think about the life cycle of GHGs, and it's a good question to bring up, the current methodology for making carbon fiber is bringing crude, a major manufacturer of carbon fiber, bringing crude from the Middle East that's being produced to Japan to process through to a propylene, then a polyacrylonitrile to be moved over to Washington State, and then be processed to be moved over to Europe for final vehicle placement. That's quite a long GHG train. So I think the detailed analysis hasn't been done on all of that. We would expect asphaltene to match closer with Route 3.
I could add to that the GHG and the energy requirements of producing either PAN or even pitch is significantly higher than the GHG and energy production of asphaltenes. What comes after that, once you have the asphaltenes or you have the pan, that's probably comparable.
Can carbon fiber production tie into circular economy so that at the end of life of product life, carbon fibers can be converted into other useful product life? What's the overall life of a carbon fiber product?
You want to take that, Axel?
Okay, the overall life of a carbon fiber product, let me deal with that first. In the case of concrete, it would be comparable to the life of a concrete. Most concrete these days is actually repurposed. It's ground up and reconstituted for new concrete. And if it has a carbon fiber content, that should not present a problem. In the case of other carbon fiber products, such as vehicles, at the end of life, you wouldn't typically recover the carbon fibers because they are long carbon fibers. You may very well be able to chop the components. You may be able to remove the resin, and then you end up with short chopped carbon fibers, which you can use in concrete and in other applications. But it is an area, the circular economy area for carbon fibers and the end of life of carbon fiber products that has not been fully examined, and I would invite listeners to think about that because it is of really major interest here in Alberta to us and to Alberta Innovates. So if you've got some suggestions of how to approach that, we'd be delighted to hear from you.
Great. How does GHG intensity of CF manufacturing compare to steel from ore and concrete from rock?
When we did the study, there didn't seem to be, I mean, when you're trying to do, I'll call it an apples to apples comparison, there didn't seem to be a comprehensive study out there. There's different people looked at different things. But if you take the steel comparison, like I think you mentioned, moving iron ore across the ocean and refining it and so forth to steel, I think a lot of it comes down to logistics. So I think there's more work that needs to be done on that.
I would add to that steel production, for example, from iron ore is directly associated with CO2 emissions because the oxygen in the iron ore ends up as CO2. There is not the equivalent when you make carbon fibers. There are energy requirements to make carbon fibers because of the heat treatment and graphitization and carbonization that was mentioned. But that's comparable and similar to the heat treatment that you have to subject steel to as you shape it, roll it, anneal it, etc. So it's a front end where carbon fibers should have an advantage over steel. And I might say other kind of commodities such as zinc and lead, for example, that are all derived from oxide ores or from sulfate ores, which are then converted into the metal.
What about other plentiful sources of carbon, example graphite as a competitive source?
You want me to comment?
Yeah, sure.
There are graphite deposits. They're really small in relationship to the oil sands, and they're really small in relationship to heavy oils are all around the world. That's not to say that they aren't valuable, but those are very specific applications.
Just in the BBC two-phase study, we split the carbon world into a microcarbon world related to carbon fibers, and there was the nanocarbon world relating to graphenes and nanotubes, and graphites with these smaller deposits is really a feedstock to go into graphenes and carbon nanotubes, as Axel mentioned. It's kind of a smaller play, but our alignment was on the bigger side on asphaltenes and moving it into big global products, and I think we felt the graphite deposits, they weren't in our interest in the bitumen context, so we didn't think it was as big an opportunity.
Is there interest in other products aside from fibers? For example, bead activated carbon or similar?
The answer is yes. Quite a number of people have looked at using asphaltenes as a precursor to activated carbon. The activated carbon market is important, but it is small in relationship to the potential market for carbon fibers in concrete, steel, and wood. There are some other possibilities. One of them are carbon foams, which enable you to make three-dimensional products, not by building up fiber structures, but by making them in 3 dimensions to start with. But that is at an even earlier TRL level, like 1.
Yeah. And I'd add on the carbon fiber markets, we covered 3 major ones here, steel, concrete, and wood. But we also, in our work on phase 2, although we didn't put it in the report, you're looking at aluminum replacement and also titanium and other strong materials as well. So there's all sorts of different places where carbon fiber can go, where it has these incredible properties.
And lest it be overlooked, carbon fibers are extensively used in the aviation sector.
Yes.
If you fly a modern plane, a very large proportion of that plane consists of carbon fibers, having replaced the aluminum, titanium, and steel components. But that wasn't the focus of our work, because the total demand for carbon fibers in the aviation sector is really small. It's very valuable, but it's very small. And we wanted to look at large applications.
10% of CF is from pitch, coal tar, or petroleum. Is anyone making CF from oil sands derived pitch, not asphaltene virgin pitch?
Not at this point in time.
What is the estimated capital required to potentially establish both a PAN facility and upgraded infrastructure at bitumen facilities within Canada and or Alberta to handle the projected demands?
We started to look at some of this, and there's some of it in the phase 2 report, where we estimate, first of all, the capital cost of extracting asphaltenes from bitumen. That's the first element. And then some costs to modify the asphaltenes and then build a polyacrylonitrile facility. We extracted costs for and then subsequently we extracted costs for the world's largest carbon fiber production facility in Moses Lake, Washington State. We put some of those pieces together. We did not have a hard number. Suffice to say, it's a capital intensive, technology intensive process at this time. So I think the subsequent stages of bitumen beyond combustion, as the study develops, I think people will put some hard numbers to those facilities. But we are starting to see more polyacrylonitrile facilities emerge around the world. But yeah, please take a read of the phase 2 report for some indications of cost in those areas. But I don't have a hard number given for a 20,000 ton facility right now.
Okay. Has any work been done to engage with concrete and steel manufacturers, i.e. CF customers, to understand that barriers to entry and development pathway to commercialize CFs? I understand the 1% market penetration assumption to show the potential and value, but that doesn't represent reality. Is this something AI will pursue?
The answer is yes, we will pursue it. Actually, there are a number of concrete suppliers and construction firms that offer carbon fiber reinforced concrete at this point in time, with the carbon fibers being derived primarily, as far as I know, from PAN. But these are very specialized types of applications. So we invite concrete manufacturers and construction companies, but also designers, architects, structural engineers, to think about carbon fiber reinforced concretes at the design phase, because the gains that can be made in terms of cost, efficiency of production, longevity of the structures are very high. But we are at the beginning. The question is 1% optimistic or not? You may think it is smaller or larger. It's easy for you to multiply what that implies. We don't really know yet at this point in time, but we thought that a 1% penetration was a realistic figure to use as a point of reference for further work.
And I would add to that, from the Alberta Innovates perspective, not only is our interest in advancing the technology as part of the Bitumen Beyond Combustion program, but also in parallel working on the marketing element as well, and ensuring that there are receptors for these technologies and these products once they become ready for commercialization. And so those are the two parallel streams that we are pushing down to ensure that we can have success with this program.
The presentation seems to imply that concentrations or extraction of asphaltenes is key to the successful manufacture of CF. To what degree does vacuum tower bottoms provide enough concentration of asphaltenes from oil sands bitumen, or is more required?
Well, the vacuum tower bottoms was the crude oil bottoms route 3, a conventional pitch route. So our context here was from looking at existing infrastructure in oil sands and looking at a diluted bitumen stream where we need to precipitate the asphaltenes out of that process, which is a technology known as the solvent extraction process. So it's comparative. Our focus is very much looking at the bitumen infrastructure that's in northern Alberta right now. So it is similar. It is similar. Although a vacuum bottom, you're looking at a distillation process, whereas this would be a solvent extraction process.
Maybe I can add to this. Current indications are that the quality of carbon fibers that you can make from a vacuum bottom, either starting with a heavy crude or even with the pitch, is of somewhat lower quality than if you start with a high purity asphaltene. Because there are fewer contaminants and constituents in an asphaltene stream than there are in a bottom pitch stream.
What are the molecular changes accomplished in making precursors from asphaltenes?
Could you repeat, please?
Yeah. What are the molecular changes accomplished in making precursors from asphaltenes?
Okay, basically what you do is you start to get some of this geometric alignment that Nathan mentioned in connection with a little insert into one of his charts. So it's the initial alignment of the large molecules that are the asphaltene molecules that the pretreatment addresses.
Just on that note, as we work on this in the future and moving it into these global commodities, and I'm thinking concrete reinforcement in particular, you're going to want to create carbon fiber strands that are fit for purpose, not necessarily have to go into, let's say, for example, an aircraft or something else. So there could be a reduction in the amount of processing that we have to get to. So it can be I'll call it a partially upgraded asphaltene as opposed to a fully molecular aligned asphaltene process. That's stuff that was got to be discovered. And there's commercial aspects to that, but there's different applications, high-end applications, very, very sophisticated requirements to perhaps lower-end global commodities going into reinforced concrete and so forth. So there's perhaps a few different levels that can be worked out there.
Has any contact been made with Honeywell, which holds the U.S. patent on making CF from asphaltenes?
We're familiar with the Honeywell patent, and we did a screen of IP in this area and the phase 2. I have not contacted Honeywell.
Neither have we at Alberta Innovates. The reference to the patent is in the BBC2 report.
It is.
What are some of the barriers you anticipate in Alberta to adopt production of carbon fibers from bitumen?
Well, like in anything else, first of all, you have to be confident of the technology, that it actually does work. And carbon fibers from bitumen or asphaltenes derived from bitumen has not yet been demonstrated on a mid-size or larger scale. So that needs to be done. The costing has to be sorted out as well. But at the same time, and I would recommend that we don't do this just in sequence, you have to get the users involved. And you can do that by using the products from small pilot plant size facilities, incorporate them into concretes and wood products and other products. So that's what is currently underway. Paolo referred to the fact that we are stimulating this work, and prior to or at the time of the next webinar, we'll make some announcements that will shed some light on that.
Do the CF quality requirements change significantly depending on application? Example, CFRC versus CFRN.
Yeah, we'd expect a wide range, and I'll come to call it the baseline concrete short fiber that goes into concrete. Sorry, carbon fiber, short fiber that goes into concrete versus something, let's say, for example, a component that goes onto the body of a Formula One vehicle. You're going to have quite a difference in that requirement. So we looked at that, and there's different elements to pitch generated carbon fiber and what would be similar to asphaltene versus the highly pure polyacrylonitrile. So there's a whole spectrum of different things out there, and I think it's fitting what we have, this feedstock, into that spectrum to see where the end use physical property sits.
So apart from the bulk properties of the carbon fibers, such as tensile strength and stiffness, you also have to think about the surface properties, because the matrix in which the carbon fibers sit is quite different whether it is a polymer or it is a concrete.
Yeah.
So we're coming to the end of the questions. If you have any more, please put them in. I think one of the questions that did come up was specifically around where this will be posted. So we do post it on the COSIA website, and I believe Stantec will post it on their website as well. So if you just come to the COSIA website under videos, it'll be posted probably within 24 to 48 hours. And I think that was it for the questions, or
There's
one more?
One more question that's
okay.
come in. As indicated in the presentation, the TRL for bitumen use as CF was at TRL 3. Have you engaged with universities and polytechnics to validate bench scale processes?
The answer is yes. Stay tuned and we'll tell you about it the next time, what the nature of the engagement is.
Okay, so that's it. So I'd like to thank you for coming today. To thank our presenters, Paolo, Axel, and Nathan. Again, our next meeting will be
January 31st.
January 31st. So please join us for that. If you have registered, I believe we'll send you out a reminder if you would like to take part in that next meeting. So again, thank you everybody, and look forward to seeing you again on the next meeting. Thanks.